So today we're going to talk about comparing ideal and real gases. For most of our purposes, the ideal gas law, PV equals nRT, works, but there are some deviations from the ideal gas law, so that when we have a gas sample under real-world conditions, maybe its pressure isn't exactly what the ideal gas law would predict. Maybe its volume isn't exactly what the ideal gas law would predict. The kinetic molecular theory, we have to remember, is just a mental model. And it imagines that gas particles themselves are so tiny that their volume becomes negligible, which is true in most cases because their volume is very tiny compared to the volume of the container, or you could say compared to the space between them. The same thing is true of their intermolecular forces. Because they have so much kinetic energy, the attraction between two particles is negligible or insignificant, because usually the particles just bounce off of each other, regardless of how much they attract, because they're traveling at such fast speeds and they have so much kinetic energy. You can imagine that at really extreme temperatures and pressures, this isn't the case. So, for example, if I bring in this little PhET illustration here, if I have a sample of, in this case, I think the gas is oxygen, and the temperature is only 31 kelvins, it's going to be a solid. The volume of the particles is significant because the particles are stacked up next to each other. The other thing is the attraction between particles is significant. So if I hit play here, the attraction is so strong at this low, I should say, the attraction is not really strong, but it's strong enough that at this low temperature of 31 kelvins, which would be like, minus 240 Celsius, the attraction is strong enough to hold them together. But if I heat this sample up at all of a sudden that attraction does in fact become negligible. So at extremely low temperatures, the attraction is negligible. At extremely low temperatures, the attraction becomes more significant because the particles aren't moving as fast, and so it's no longer negligible. Now, when we bring it up closer to room temperature, so here we are with oxygen at 270, 280, 290. So now we're at about room temperature, about 294, 21 degrees Celsius. And now the attraction is negligible because the particles are bouncing right off of each other. They're not forming drops of liquid oxygen. The same thing is true with pressure. At normal atmospheric pressure, which we're not even at that, we're at much higher than that in this simulation, but at relatively low pressures, the particles are not interacting enough for those attractions to take over. But if I increase the pressure, the interactions become more frequent and therefore more significant. And if I double the number of interactions simply by raising the pressure, which I'm doing in this case by decreasing the volume, the attraction between particles, those van der Waals forces, become more and more significant. And eventually this oxygen, even though it's not at its normal freezing point, not at its normal boiling point, would condense into a liquid. So it's kind of understandable how gases can act unlike the kinetic molecular theory predicts at really low temperatures and at really high pressures. But it turns out that even at room temperature, the pressure we see, we see slight deviations from the ideal gas law. In other words, from the kinetic molecular theory. It doesn't quite hold up. We might only be off by 1 or 2 or 3%, but it's still significant enough to talk about. And van der Waals equation, if you remember, of course, van der Waals forces refer to those forces of interaction. And because it is the volume of the particles and the attraction that the particles have for each other that causes deviation from the ideal gas law, it should kind of make sense that it's van der Waals equation that we're going to use to account for attractions between particles. So van der Waals equation essentially says, instead of just, and I'll rewrite the ideal gas law just so you can see it, P times V equals N times R times T, we are going to change the pressure a little bit. So instead of just P, we're going to say pressure plus number of moles squared times A, which is a constant that I'll give you in just a second, divided by volume squared. And then instead of V, I'm going to replace that with volume minus number of moles times another constant. And then the rest of it just stays the same, N times R times T. So we've got two constants introduced here, A and B, and I'll show you those. So A, which is in the pressure part of our equation, has to do with the amount of intermolecular attraction. And so as we look at a couple of different molecules, and this, you'll be given these, of course, as is the case with all constants. And this actually comes from your textbook. I know we haven't used it in a while, but you have this table on page 161 in your textbook. But anyway, if we look at A has to do with the attraction between particles. So things that have lots of hydrogen bonding, things that have, that are polar, like, for example, if we look at ethanol, it's got this hydrogen bonding, it's got this huge constant value for A. And that's because A accounts for the attraction between particles in van der Waals equation. So when I look at A right here, we're talking about attraction between particles being accounted for and affecting the pressure. Okay? So something like carbon dioxide is nonpolar, but it's a little bit, more polar, obviously, than something like helium. So its value for A is going to be quite a bit bigger than helium, which is a noble gas and about as nonpolar as you can get. And then something like ethanol that has hydrogen bonding has this huge value for A, 12.56. Water has hydrogen bonding as well, so 5.537. And then B accounts for the volume of the particles, or helps to account for the volume of the particles, which is why it's being subtracted from the total volume of the container. So if we look at our table for B, we get larger values for larger molecules. So helium has a really small value, water's a little bit bigger, ethanol is very large because it's a much larger molecule than these others. It's a little bit more complex than just like molar mass, because it has to do with not only the mass of the particles, but how much space they would take up. So if you look at the Lewis structure for these, it also tells you something about how much space they're going to take up, not just look at, it's not important just to look at their masses. Okay, so let's take a look at an example. Okay, we're going to start by solving the problem using the ideal gas law, and then try using van der Waals equation and see, kind of look at what the difference is. Okay, so if I just use the ideal gas law, what pressure do we expect SO2 to exert if we have 1 mole of it and its volume is 22.4 liters at 0 degrees Celsius? Well, if I use PV equals nRT, I'm looking for P, right? So P equals nRT over V. Now I can plug in all my numbers, but N is going to be 1 mole. R, let's say we're looking for pressure in atmospheres. R would be 0.0821. Temperature would be 0 degrees Celsius or 273 kelvins. And volume is 22.4 liters. And we should know just by looking at this that the pressure should be 1 atmosphere. And that's because we have 1 molar volume and we are at standard temperature, so we should also be at standard pressure. So we don't even really have to use the full ideal gas law, but we could. But our answer should be 1.0 atmospheres. Okay, but now if we apply van der Waals equation, this is a little bit different. So van der Waals equation, we have it up above. So P plus number of moles squared times A over V over volume squared. So we're going to plug all that in. So, and if I go ahead and take my original equation and say, which was P plus N squared times A over V squared times V minus N times B equals nRT. And if I'm trying to solve for P, let's think about what we might have to do. Okay, so if we're going to get P by itself, we have to divide both sides by V minus NB. So I get V minus NB. If I do that to both sides, it just cancels on the left. And then I'm going to subtract N2 times A over V2. So you get that. And so that takes care of that. And so I get a new equation that says that pressure is equal to nRT over V minus NB minus N2A over V squared. All right, so, or I should say N squared times A over V squared. And so now it's just a matter of plugging in my values. To do that, we're going to have to give you the constants here. And the A value for SO2, sulfur dioxide, is 6.865. And that is liters squared times atmospheres over moles squared. And our B value for SO2 is 0.05679. So 0.05679, and that is liters per mole. And this, again, these both just come from the table that I showed you earlier. And again, you'll be given this table for all problems. So with all of that, let's see if you can plug in everything and solve the problem. Okay, so there's your setup. Just brought everything down. Number of moles is 1. R, since we're in atmospheres, is 0.0821. Temperature 273. Volume 22.4. Number of moles, which was 1, times the B value, which is 0.05679, minus number of moles squared, so 1 squared, just 1, times A, which was given to you, and then divided by volume squared. So if we work this out very carefully, because there's a lot of stuff you could potentially mess up, but we should get a slightly smaller pressure of 0.989 atmospheres. So it did go down a little bit. And if we think about what that means, and I guess that's actually 2 sig fig, so I should have said 0.99 atmospheres. So the pressure did go down a little bit from what the ideal gas law would predict. And if we think about that, the reason is the particles are attracting each other. And if the particles are attracting each other, that's going to decrease the number of collisions that they have with their container, right? So there's a slight little, 1% difference, give or take, once we round for sig figs, between what the ideal gas law predicts and what we would calculate using van der Waals equation.